Let's begin by understanding the concept of properiodic points in dynamical systems. A point is called properiodic if after a certain number of iterations under a function, its orbit becomes periodic. For example, if we look at the function f(x equals x2, 1, the point x0, 1 has an orbit that cycles through 1, 0, minus 1, 0, minus 1, and so on, making it properiodic. Similarly, x0 equals minus 1 for f, x equals x2 quickly becomes fixed at 1, which we call an eventually fixed point. These examples show how orbits can settle into repeating patterns or fixed values, and this behavior is foundational for exploring more complex dynamical systems. As we move forward, we'll see how even simple functions can produce surprisingly intricate orbit structure. Now let's explore the doubling function, a classic example in dynamical systems. The doubling function dx maps 0, 1 to itself by doubling and removing the integer part. Rational numbers under D have orbits that eventually repeat, making every rational number properiodic. For instance, the orbit of 1, 3 alternates between 1, 3 and 2, 3, forming a 2-cycle. However, when we try to compute orbits using decimal approximations, errors double with each iteration, quickly leading to inaccurate results. This sensitivity to initial conditions highlights a fundamental challenge. Even with powerful computers, numerical methods can struggle to accurately track orbits, especially for irrational starting points or chaotic systems. This sets the stage for understanding why chaos is so difficult to predict and analyze. To better understand how orbits behave, we can use graphical methods. By plotting the function y equals f, x alongside y equals x and tracing the orbit of a starting point, we create a staircase pattern that visually represents the sequence of iterates. For example, with fx equals x plus sin, x plus 2, the orbit moves steadily to the right, while for fx equals sqrt x, orbits approach the fixed point at equals 1 from both sides. These visualizations help us see convergence, cycles, or even chaotic wandering, as in the case of the logistic map. Sometimes the orbit appears to meander unpredictably, a hallmark of chaos. Graphical analysis is a powerful tool for gaining intuition about the qualitative and quantitative behavior of dynamical systems. Next, let's discuss Newton's method, a powerful algorithm for finding roots of differentiable functions. Starting from an initial guess, Newton's method uses tangent lines to iteratively approach a root. For example, to approximate sqrt2, we use the function fx equals x2, 2, and the sequence quickly converges to the correct value. However, the method's success depends on the starting point and the function's properties. If the root has higher multiplicity, convergence may slow down, and if the derivative vanishes or is infinite, the method can fail or behave unpredictably. Newton's method not only helps us find fixed points but also provides insight into the dynamics of iterative processes, revealing both stability and chaos depending on the context. Finally, let's consider the concept of multiplicity and its impact on Newton's method. The multiplicity of a root determines how quickly Newton's method converges. Simple roots lead to supertracting fixed points while multiple roots slow down convergence. The theorem guarantees that, for roots of finite multiplicity, Newton's method will converge if started close enough. However, the region from which convergence occurs, the attracting basin, can be quite complex, especially for functions with multiple roots or undefined derivatives. In some cases, as with functions lacking real roots, Newton's method produces orbits that never settle, illustrating the rich and sometimes unpredictable dynamics at play in even simple iterative systems. This interplay between algebraic properties and dynamical behavior is at the heart of chaos and fractal systems.